So good evening everybody, and thank you for the invitation to come and talk to Northamptonshire Natural History Society. So this, as you can see from the title, is the ABC, what I tend to think of as the ABC of stellar evolution, the three principal things that we have to think about to understand how stars are born, how stars live, and how stars die. So those are the three categories that I'm going to talk about this evening. And within each of them, I'm going to say a few things. I'm going to talk about what's going on at the heart of stars. I'm not going to turn it into a nuclear physics lecture, you may be glad to know, but we need to understand nuclear fusion to understand where stars come from in terms of how they're born. When it comes to the lifetime of stars, we're going to look at the balance between radiation and gravity. And the idea that large stars burn their fuel very rapidly, hence the mantra of live fast, die young. And we'll ask the question, what happens when the fuel runs out and a star comes to the end of its life? Do they end with a bang or a whimper? If they end with a bang, what's left afterwards? And if gravity ultimately wins, then we end up perhaps with a black hole. And I'll say a few words about that at the end. So first, let's get an idea of the life cycle of a star such as our Sun, just to give us a sort of frame of reference, as it were. This is the number of billion years since the Big Bang, so there's the Big Bang on the left, and a separate talk talks about how all the hydrogen in the universe was made in the first 3 minutes after the Big Bang. We are currently now at about 13.8 billion years, taking the Big Bang as zero. And I'm looking a few billion years into the past at the birth of our Sun. Our Sun is assumed to be about 4.5 billion years old. So that's when our Sun condensed out of a hydrogen cloud. And so now the Sun is approximately middle-aged. It's quite a few billion years old, and it's got quite a few billion years left before it starts to get towards old age, and we'll see shortly how that leads to the Sun becoming a red giant. So the Sun will expand, its mass will not change significantly, but it will expand, and after the outer part of the Sun has blown away, we're left with a very hot white core, which is a white dwarf. So the Sun is going to look very different in a few billion years' time, firstly expanding and then living out the rest of its life as a small white dwarf star. Bear in mind, none of these circles indicated here are supposed to indicate true relative size. This is not to scale. This is just a rough idea of our thinking about timelines. For a star like our Sun, timelines are typically in billions of years. As we'll see shortly, for smaller stars and larger stars, the timelines can be quite different. So what's going on in the heart of a star? Well, I'm sure you are aware of the fact that at the heart of a star, nuclear fusion is giving us an energy source. So in other words, a number of hydrogen atoms, let's just represent them as little red golf balls, the nuclei of a hydrogen atom, 4 of those can fuse together to make the nucleus of a helium atom. So I'm not going to be talking about atoms, I'm only going to be talking about nuclei. It doesn't really matter what the electrons are up to, it's just the nuclei that are important. And the bottom line is that given enough pressure and enough temperature, we can fuse 4 protons, 4 hydrogen nuclei into 1 helium nucleus. And that process is going on second by second. Every second of the Sun's life, some 600 million tons of hydrogen are being converted into 596 million tons of helium, the numbers at the bottom there. And the 4 million tons that is lost, in inverted commas, that mass is converted to energy. So one thing to bear in mind is that the star is not getting smaller and smaller and smaller and smaller as it's using up its nuclear fuel. To a rough approximation, to the nearest percent or so, the amount of matter that's left after the nuclear fusion is the same as before. 600-ish million tons are converted into 600-ish million tons. Only a tiny amount of matter is actually lost in the process of generating all the energy that the Sun produces. So stars are not simply nature's way of lighting up the universe. They are effectively fusion factories. This is how the elements are made, or at least the elements heavier than the matter that's made in the Big Bang, where a lot of hydrogen and some helium were made. In terms of all the heavier elements, that's basically the fusion factories of stars. Producing light, in a sense, is just a byproduct. You could say, yes, right, we're converting hydrogen into helium, but where does all the hydrogen come from? That's not something I'm going to address in this talk, because it is an entirely separate talk to ask, how did the universe make all of that hydrogen in 3 minutes? So I'm not going to address that, but happily talk in the Q&A if you so wish. So we ask ourselves, where do stars come from? But making a star is easy. Anybody can make a star. All you need to do is to follow these 5 very simple steps. 1. Start with a very large cloud of hydrogen. 2. Wait. 3. Wait some more. 4. Wait a bit longer, and that's it. You're done. Now you have a star. In other words, if you start with enough hydrogen and you just let gravity do its stuff, you will end up with a star. It's essentially inevitable if you start with a large enough mass in the first place. So this, of course, is the Orion Nebula, a lovely stellar nursery, a large cloud of hydrogen, perhaps seeded with a few other elements in there, which I'll come back to a little later. But we can ask ourselves, okay, we have a large amount of hydrogen, but what triggers the collapse? What triggers gravity to take hold and start to compress the large cloud of hydrogen? Well, there are lots of these clouds floating around the galaxy. They're called giant molecular clouds. And they're called that for 3 very good reasons. 1, they look like clouds. 2, they consist of hydrogen. And 3, you can see where I'm going with this. Yep, 3, they're large. Many tens of light years across. Perhaps of order 100 light years might be typical for a large hydrogen cloud. And we can ask ourselves, what is it that triggers the collapse? Gravity wants to pull this cloud and condense it, but usually some trigger is required to get that process started. What sort of triggers are likely to get star formation going? Well, these clouds are effectively floating around the galaxy, orbiting the centre of the galaxy like most of the stars do. Every once in a while these clouds are going to collide with each other, and the collision of 2 molecular clouds can be enough to start the process of collapse, of gravitational collapse. It's also possible that shock waves rippling through a cloud can trigger star formation. Where might those shock waves come from? Well, perhaps the death of an earlier star might produce shock waves that ripple through a cloud and actually trigger new star formation. So the death of one star can actually trigger the birth of new stars. And thirdly, another possibility is galaxy collisions. That sounds very dramatic because you tend to think of one galaxy ploughing into another as being a rather devastating, catastrophic situation. But actually that's not the case. It's a perfectly natural part of galaxy evolution. The fact that galaxies collide with each other and merge with each other is part of how galaxies grow. When we look at a galaxy like this, we see a large and a small galaxy that appear to be interacting with each other, and all of the pink we can see in the spiral arms of this galaxy are new star-forming regions. And it's particularly dramatic when we look at galaxies that we can see are in collision, such as the antenna galaxy here. You can see the red rectangle shows the 2 galaxies colliding, and perhaps you can also see these faint tails, these tidal tails that are the result of the gravity of one galaxy interacting with the other. If we look at a much more detailed view of what's going on inside that red rectangle, we see these 2 galaxies looking rather mangled, but again we note that there's lots of areas of pink here, indicating that there are large clouds of hydrogen just ripe for gravitational collapse and new star formation. So far from galaxy collisions being the end of life of a galaxy, you could argue that that's effectively a rebirth and a trigger for new star formation. If we think of what happens when 2 galaxies collide, we can take a simplistic if simulation such as this. It might be similar to the Milky Way colliding with the Andromeda galaxy. We can see that as soon as they come close and as soon as they pass through each other, tidal forces disrupt the structures within those galaxies. It's very unlikely that any two stars are going to directly collide with each other, but all of the gas in one galaxy is going to mix with the gas in the other galaxy, and it's going to trigger a huge amount of star formation. So when the Andromeda galaxy eventually collides with the Milky Way in a few billion years' time, again there'll be an enormous increase in the amount of new star formation. But let's think about how we know what goes on. Let's try and simulate what happens when a cloud of hydrogen collapses. This is a simulation carried out at the University of Exeter. They started with a spherical cloud of hydrogen. Okay, clouds aren't necessarily spherical, but the computer simulations simply find it easier to start with that. So this is a large cloud of hydrogen, many tens of light years in diameter. And it's not perfectly uniform. It's deliberately seeded with a little bit of variation in density to give gravity something to grab hold of, and each little part of this cloud is given a random nudge in a random direction just to simulate a more realistic cloud in our galaxy. So we start with that. We know what the gravitational forces are for any two masses. We just need to know what those two masses are and the distance between them to calculate the gravitational force, and we just let the time run for a few million years and see what this cloud does. The brighter regions of this simulation indicate denser parts of the cloud. You can see the cloud is already becoming rather ragged and is starting to get rather dense at the centre. Higher density and higher temperatures as gravity collapses this hydrogen cloud. And when the temperatures are high enough and the pressures are high enough, then individual nuclei of hydrogen can fuse together. As long as we have enough density and enough temperature, they can fuse and start the ignition process of a star. And you can see we're already starting to see what looks like a popcorn machine spitting out individual white dots, stars that are born from the collapse of this hydrogen cloud. Some of those stars stay fairly close to the centre where they're born. Some of these stars, due to gravitational interactions with other stars, are getting thrown out of this collection. We must have started with enough hydrogen not to make just a few dozen stars. It looks like we started with enough hydrogen to make thousands of stars into a star cluster. If we back off a little bit and do a little twirl, we can see that the original spherical cloud looks now very ragged, but there's still quite a lot of hydrogen there. We haven't used up all of the hydrogen in this cloud in order to make all the stars that we can see in this cluster. Lots of stars now in the centre, some stars spread out, some stars lost completely from this cluster. So that's what we get from a simulation. Does that bear any resemblance to the sort of star clusters that we see if we look out into our night sky and look at star clusters, not the globular clusters here of the distant parts of the galaxy, but the more open clusters, the galactic clusters? Does that sort of give us a reasonable indication of what they look like? Well, yes, I think you'll agree that when we look at real star clusters, it seems plausible that the sort of simulation we've just run does explain the creation of star clusters with perhaps quite a few thousand individual stars. It's quite probable that our Sun was born in a star cluster, even though now, of course, it's a lone star on its own, but it was probable that the Sun was born in a cluster like this and was one of those stars that got thrown out very early on. Because that happened 4.5 billion years ago, it's effectively impossible to backtrack and try and work out which cluster we might have been born in at the time. All stars are a question of balance. In the most simple way we can think of a large ball of hydrogen with nuclear fusion at the core, gravity is always trying to compress the sphere into a smaller structure. And at the heart, as we've seen, that's where it's hottest, that's where it's densest, that's where the nuclear reactions will start, and fusing hydrogen into helium releases energy, and so radiation is pouring out of the core of the star. And a star in balance, where the inward forces of gravity are balanced by the outward forces of radiation, when a star is in balance, the star is stable, the star is happy, and hopefully, if the fuel doesn't run out, that star could continue in that way, producing radiation which balances gravity. It could be millions, it could be billions, it could be trillions of years that balance is maintained. We'll see the differences for different masses in just a moment. But the important point about balance is, as long as gravity and radiation are in balance, the star is stable. If, for any reason, gravity and radiation get out of balance with each other, the star must evolve. Whenever you get an imbalance, the star must change. And I would argue all aspects of star birth, star life, and star death can be thought of in terms of this balance and what I like to think of as the ABC. The B we've already seen. The B is balance. And the rest of the ABC we will see here. When it comes to fusion, for instance, two hydrogen nuclei, two protons, they're both positively charged, so they want to repel each other. So you can't get them to fuse unless you have high enough pressure and high enough temperature to overcome the electric repulsion of two positively charged particles, and then we can actually get fusion to occur and energy to be released. So if you can raise the temperature and raise the pressure, you can accelerate the rate at which fusion takes place. So A for acceleration. B, we've already just seen that. The crucial aspect is balance. If it's in balance, nothing much changes. If it's out of balance, something must change. And finally, the C of the ABC is that if a star compresses, compression produces heat. There's no surprise there. Anybody that's ever pumped up a bicycle tyre knows that when you compress air to take the air into a bicycle tyre at a pressure that's higher than the ambient pressure, the pump and the air inside the tyre get hot. So that's it. That's the A, B and C. If we understand those A, B and C, then we pretty much understand how stars are going to behave. Balance, everything's fine. If it's out of balance, compression produces heat. If we have heat, we can accelerate the process at which fusion takes place. Let's just remind ourselves how stars are classified, because that's useful for what's going to come next. If we plot stars on a diagram of luminosity, this is not how bright they appear in the night sky, but how luminous they actually are. How luminous they are on a scale of 1 is equal to the sun. And on the horizontal scale, we plot the surface temperature of a star. That helps us sort of classify different types of star. So there's our sun there. By definition, it has a luminosity of 1. And its surface temperature is a little shy of 6,000 Kelvin, or roughly 6,000 Celsius. So we'll see some of the other stars in this luminosity colour diagram, or Hertzsprung-Russell diagram, shortly. So let's consider what happens if we have a hydrogen cloud collapsing to produce a relatively massive star. Different mass stars follow different lives. And by high mass, what I mean is a mass a fair bit bigger than the sun. Let's take the mass of the sun as a useful unit. What if the mass of the star was some 10 times the mass of the sun? Well, then we've got an awful lot of fuel, of course. We've got 10 times as much fuel. And you might at first think, well, if there's 10 times as much fuel, then isn't the star going to last longer? Isn't it going to burn its fuel for longer? Well, no. Gravitational forces are much stronger when we have a more massive star. And if gravitational forces are stronger, that means because we need the star to be in balance, we have to burn fuel very rapidly to generate the radiation which is pushing outwards to balance that in-pulling gravity. So that means we have to actually burn our fuel very rapidly. And far from being, well, there's lots of it therefore it'll last longer, it's just the opposite. High mass stars will only live a relatively short length of time. Unlike our star, which might last for many billions of years, a lifetime of perhaps 10 billion years, high mass stars might only live for a few million years, substantially shorter lifetimes. And if we take the opposite of live fast, die young, Low mass stars, they don't have a lot of fuel, so we might naively expect if there's not much fuel, they perhaps don't last long. But no, the critical thing is the balance. The gravitational forces are relatively weak in low mass stars, so because gravity is relatively weak, we don't have to burn the fuel particularly quickly in order to produce the radiation pressure that keeps the star in balance. And hence, even though there's not an awful lot of fuel, the fuel lasts for an awful long time. For instance, if we were to take a star, let's say 1/10 of the mass of the Sun, we can calculate how long we expect those stars to live, but we can't actually verify it because we might expect those stars to last for trillions of years. And the universe isn't that old yet. So a lot of low mass stars born in the very early universe are probably still quite happily living out their lives because they will last for much longer than the current age of the universe. So a lot of this is hypothetical in the sense it's based on our understanding of how stars work rather than our observation of what we can see from low mass stars. We just assume that they will last for trillions of years. Let me just take a very quick diversion, because what really matters in stars is the mass. Are they mass of 1/10 of our Sun, or a mass of 10 times our Sun, or a mass similar to our Sun? Masses tend to vary by a little bit, a factor of 10 or at most a factor of 100 relative to a star like our Sun, which is a fairly typical middling star. But in terms of how large a star might be in terms of its radius, those can vary quite considerably. So just as a little diversion, let's just think about what the size of stars can be. The masses don't vary much, but the sizes can vary substantially. As a starting point, let's just remind ourselves about objects in the solar system. Here, not arranged by distance from the Sun, but arranged by size of the object, from Mercury to Earth. And then the next panel, Earth is down there in the bottom left-hand corner, down here on the left. And then we've got the larger planets to scale with Earth. So each panel has the objects to scale, but each panel will be a different scale as we progress upwards. There's Jupiter on the right-hand side at the bottom of that panel. Let's now put Jupiter there in the bottom left and think about the size of stars. You can see that one of the smallest stars, Wolf 359, is apparently not that much bigger than Jupiter. It only appears to be some twice the diameter of Jupiter, which is why sometimes Jupiter is referred to as, in a sense, a failed star. If Jupiter had a rather larger mass, it might have had a sufficient mass to actually undergo thermonuclear fusion at its core, but Jupiter isn't quite there. Wolf 359 is somewhat smaller than our Sun by a factor of 10 or so, and you can see that our Sun is rather smaller than the star Sirius, with a diameter of perhaps twice our Sun. Let's do the same. Let's take Sirius and make that the smallest object in the next panel. So there's Sirius and a few stars you might recognise: Pollux, Arcturus and Aldebaran. You can see Aldebaran is huge compared to Sirius, which is already twice the size of our Sun. So you can see that even if the masses don't vary that much, the physical size of stars already, we can see, have varied quite substantially. But we're not done yet. Let's take Aldebaran and squeeze that down to the start of the next panel, and then we'll see that Aldebaran looks tiny compared to Rigel, compared to Antares, and compared to Betelgeuse, these huge red supergiants. So given that the mass hasn't changed that much, we deduce that if these stars are really large, but not that large in terms of mass, then these large red giant stars are rather low density objects. Still not done yet. Let's take Betelgeuse and make it the smallest object on the next panel. And then we see some of the really largest stars that we know about. I don't know if VY Canis Majoris still holds the record. It did when this particular panel was put together. I believe they've now found a few stars that are slightly larger, but the largest stars we know about in terms of their radius are comparable to the star VY Canis Majoris, which is, as you can see, large even compared to Betelgeuse. And it's difficult to draw a direct comparison of our Sun to these large stars, but I'll have a go. There's our Sun, and there's an arrow to make sure you can see it, and there's VY Canis Majoris. And if you're having trouble seeing VY Canis Majoris, let me bring it in. There it is. And by the way, this is an exaggeration. I haven't exaggerated the size of VY Canis Majoris. I've actually exaggerated the size of the Sun, because if I put the Sun to true scale, it would probably be smaller than 1 pixel on my monitor, or 1 pixel as transmitted by Zoom. So you can see that the relative volumes of a typical star like our Sun and the largest supergiants like VY Canis Majoris are absolutely vast. So it might only be 100 times bigger in mass, but the volume is, I don't know how many millions or billions of times larger. A reminder that some stars are very low density. Okay, so the physical size is a slight red herring, in the sense that really what matters is how much mass is there, because mass determines gravity, and gravity determines the balance of gravity with the fuel, and hence what happens when the fuel runs out is a question that we have to address at different times depending on the mass of the star. So let's see how that works. So I'm going to talk about nuclear fusion, but I'm going to occasionally talk about burning. Burning is just a little bit of colloquialism, meaning burning in the sense of nuclear fusion, burning hydrogen to make helium, not burning in the sense of, in Earth's atmosphere, burning something in the presence of oxygen to make a flame. This is nuclear burning, and so that's just a word that's used by nuclear physicists occasionally. So remember that nuclear fusion doesn't use up much of the star's mass. Virtually all the mass at the end of a star's life was there in the first place. Only a tiny fraction is actually lost in the process of nuclear fusion. Remember, in the case of our Sun, it was something like 600 million tons of hydrogen is converted into 596 million tons of helium every second. The difference is crucial. That 4 million tons that is lost, that is what is responsible for all the heat and light from the Sun being spread throughout the solar system. But we have to remember that even when our Sun comes to the end of its life, 99% or more of the Sun's mass is still there. It's been changed from hydrogen to helium, but 99% of it is still there. It's not like it's lost half its mass because we've used a huge amount of the fuel reserves. So we can ask the question, yes, as the Sun comes towards the end of its life, what happens when the hydrogen starts to run out? Okay, that's where the ABC tells us how to think about star evolution. When the hydrogen runs out, the radiation starts to drop because the nuclear fuel is no longer providing the outgoing radiation that provides a radiation pressure, if you like, to counter the incoming gravitational forces. So the hydrogen runs out, the radiation starts to drop. If the radiation starts to drop, then we're now out of balance. We no longer have radiation balancing gravity. So if the star is out of balance because gravity is now greater than the falling radiation pressure, that means the star shrinks. What happens when the star shrinks? Well, compression produces heat. So what does that mean? That means although the fuel has run out and it's no longer hot enough to fuse hydrogen into helium because there's virtually no hydrogen left, compression has heated to the core, which means it's now hot enough not to fuse individual nuclei of hydrogen, it's now hot enough to take separate nuclei of helium, and to take one helium and another helium and start to fuse those together. It takes higher temperatures and higher pressures to fuse helium, but you can then start to talk about helium fusing into heavier elements still. And that fusion produces energy, and the radiation then balances the incoming forces of gravity, which means balance is restored. So that's how the ABC works. If the fuel runs out, gravity wins because you're no longer in balance. That compression produces heat, which accelerates the fusion of heavier elements, and we're back in balance again. So helium might be fused into carbon, for instance. What happens when that runs out? Well, this cycle goes round again. When the fuel runs out, compression produces higher temperatures, which means heavier elements can fuse. Can this just go on forever? Hydrogen making helium, helium making heavier elements making still heavier elements? At what point does that cycle break down? Well, to answer that, we need to understand something about how stable a particular nucleus is. For instance, this nucleus of helium is a very stable structure. And by stable, I'm talking about how much energy can we get out from the fusion process. And by looking at nuclei here on Earth, we have found that certain nuclei have certain stability. In other words, how much energy does it take to make a particular nucleus? By taking individual protons and neutrons, when we make a nucleus, how easy or difficult is it to make a nucleus? So we won't worry about the numbers here other than to think about nuclear mass as, well, let's just think about how heavy it is compared to the mass of hydrogen. If we were to start with hydrogen and take hydrogen and fuse it into the same amount of helium, in other words, what if we were to take 1 kilogram of hydrogen and fuse it into roughly 1 kilogram of helium, the amount of energy we get out depends on the vertical distance between these two dots. So nuclear energy here means if we're going up the slope, this is how much energy comes out of converting hydrogen into helium. So this green line is a measure of, if you like, how efficient is the process of fusion. Helium there, roughly speaking, at number 4, because helium is 4 times the mass of hydrogen. And if we can imagine the cycle continuing, what if we were to take helium and make something heavier? For instance, what if we could fuse helium into carbon, a heavier atom with a heavier nucleus? Well, 1 kilogram of helium can make 1 kilogram of carbon, but notice that the vertical height here, the amount of energy that we can expect that 1 kilogram to produce, is less. So in a sense, fusing 1 kilogram of helium is less efficient than fusing 1 kilogram of hydrogen. Even with the same amount of stuff, we get less energy out. And the same is true if we start with carbon and fuse into heavier elements, such as neon. Again, the vertical height is less because this green line is starting to tail up. And we can do the same to make silicon, but again, less energy. And we can go all the way to the top of that curve. And we have found here on Earth, and there's no reason to think it's any different in the heart of a star, we have found that iron is the most stable nucleus. In terms of how much energy does it take to make an iron nucleus, you can see that if we wanted to take silicon and fuse it to make iron, we get very little energy out. There's very little benefit to be found from fusing silicon into iron. And then we can look at that curve and say, well, yeah, but how do we go beyond iron? Because the curve now, instead of going up telling us this is how much energy release we get by the fusion process, we can imagine that if we somehow manage to fuse iron into something else, we're now on the downward slope. It doesn't release energy, it takes energy to make heavier elements than iron. And I've just picked out a couple at random, silver and gold, for instance, roughly in the right position in terms of how massive they are compared to hydrogen. So this curve, which is found empirically from measuring nuclei here on Earth, tells us that inside a star we might expect hydrogen to make helium, and if the process continues, helium to make carbon, and if the process continues, carbon to make neon, etc. But we can't expect it to go beyond iron. And a consequence of the fact that this curve is turning over, remember, hydrogen to helium is quite efficient, but helium to carbon is less efficient, and carbon to neon is less efficient, etc. If we ignore the tiny mass losses and just ask ourselves, how much energy are we going to get out of the nuclear fusion of 1 kilogram of fuel? Well, for a given star, let's say a hypothetical star, let's imagine that there's enough fuel such that hydrogen can fuse into helium and there's enough fuel to last millions of years. by the time that is done, there is still, roughly speaking, the same amount of fuel. Remember, the amount lost is barely 1%, a fraction of a percent. So if we take the same amount of helium as the amount of hydrogen we had in the first place, it's less efficient to fuse helium. So if we want to keep this star stable, if we want to keep the radiation pressure high enough to counter the gravitational pull of the star, we'll have to burn that fuel. We'll have to fuse helium into carbon on a smaller time scale. The fuel might only last 500,000 years, simply because we get less energy out per kilogram of fuel, less bangs for our buck, if you like. If we have to start fusing carbon into heavier elements, again, the same amount of fuel won't last very long because we have to burn it so rapidly to keep that radiation pressure up. It might only last 5,000 years, even though we've got the same number of kilograms, roughly speaking. Neon to oxygen, less efficient still. The fuel might only last 10 years. Oxygen to silicon, less efficient still. The fuel might only last 5 years. When it comes to that last stage of making iron, even though we've got as many tons as when we started, it's so inefficient the fuel would have to be burnt at the rate of only days to use up the entire fuel reserve to make iron. And we can't go beyond iron. So you can see that there's this sort of avalanche when things are getting more and more and more rapid, things are getting more and more and more desperate as the star is trying to burn its nuclear fuel to fuse these elements, and each time it goes through a new set of elements, it has to burn and fuse that set of elements even faster to try and maintain the radiation pressure. If we think about the periodic table of the elements, let me just dim that down a bit because it's a bit garish. So we know that the Big Bang created hydrogen, top left, and helium, top right. And we're interested, for instance, we're very grateful to the fact that some stars have been burning and fusing helium to make carbon and nitrogen and oxygen and other elements, because of course if our sun didn't have carbon and nitrogen and oxygen and phosphorus and calcium, etc., then we wouldn't exist in the form that we are currently in. So we're very grateful for the fact that some star that existed before our sun existed created these elements, and would have created a number of elements up to iron, and there's iron in the periodic table, only about 1/3 of the way through the entire periodic table. So the life of stars only explains the elements up to iron. It can't explain just picking a few at random, silver or gold, for instance. And of course, there's a whole shed load of other heavy elements which we're familiar with. Copper, nickel, cobalt, lead, for instance, titanium, platinum. All of these materials can't have been made in the lifetime of a star. So, just to recap, we know this set of cycles continues up to iron. Fusion of iron does not release energy because iron is at the top of that curve and would need an input of energy to make anything bigger. So how can we explain elements beyond iron? We can't explain it from what I've said up till now because the life of stars doesn't explain elements beyond iron. We need to go beyond star life and look at star death. So let's think about what happens for a medium mass star. Medium in this context means, let's say, around about the mass of the star, not the mass of our sun, not significantly more, not significantly less. So for a star like our sun, gravity may not be strong enough to hold on to the outer layers. When helium starts to burn in the core, when helium is starting to produce carbon, the gravity, because the mass is not particularly large, the gravity may not be enough to stop the outer parts of the star expanding, and they will expand and cool and redden. So the star becomes a red giant. So in other words, this part here. So we can see the luminosity is higher than the sun simply because the red giant has a much larger surface area, and luminosity depends on how much energy is coming out of the total surface area. If the surface area is larger, the luminosity will generally be higher. But it's further to the right than our Sun, because on this temperature scale, where cool is on the right and hot is on the left, the red giant has a lower surface temperature, perhaps around 3000 Kelvin rather than 6000 Kelvin. So red giants are up there to the upper right part of our Sun in this Hertzsprung-Russell diagram. Not only does the outer part of the star expand, but it is not that uncommon to find that when helium is being fused into carbon, the whole process is unstable enough that the star simply cannot hold on to that outer atmosphere that's been sort of puffed up, if you like, during the expansion of the red giant phase. And the outer part of the star can be lost completely to the interstellar medium. What's left used to be the core of the star. Once the outer layers have left, then the core of the star is now the star that is left. So the outer part of the star then becomes what we call a planetary nebula, and what's left we label a white dwarf. And white dwarfs are down here. They are the hot core of the star that's now been exposed by the fact that the outer layers have been blown away during the red giant phase. So white dwarfs are quite small, so with a small surface area they're not particularly luminous, hence they're lower down in this diagram, but they are quite hot, which means they're further over to the left than the Sun. So red giants in the upper right, white dwarfs in the lower left. And the outer part of the star that's been blown away, in an image like this, you can see why they were mistaken for planets in the early days, called planetary nebula because some of them looked rather circular and gave the impression of a planetary disk through a small telescope. We know that they have nothing to do with planets. They are the outer atmospheres of stars that have been lost when the gravitational pull simply wasn't enough to hang on to them. Some planetary nebulas are rather complex, depending on the spin of the individual star and perhaps whether the star was part of a binary system when the outer envelope was released. This is one of my favourites, the Helix Nebula in the constellation of Aquarius, seen low down in the south during the summer months. This particular picture is from the Hubble Space Telescope, but I tried photographing it without a telescope, just with a camera and telephoto lens, and you can see the actual structure of the planetary nebula. This is a reminder that these planetary nebula, you don't need a telescope in order to image them, which means that they are actually quite large things on the sky. The Helix Nebula is, if I remember rightly, something like half the size of the full moon. It is not a small object. Some planetary nebula that are quite distant do look quite small through telescopes, but this particular one is actually quite a large chunk of sky. So the Hubble Space Telescope has shown an enormous amount of detail, and of course this is quite interesting for us because eventually our Sun will go through this phase. Our Sun will become a red giant, it'll puff off the outer atmosphere, and it will produce something similar to what we're seeing here in the Helix Nebula. What about high mass stars? Well, it is possible with a high mass star with a very strong gravity, it's not going to lose its outer envelope into a planetary nebula as our Sun would. With high mass stars, the strength of gravity is such that the entire star will basically keep its integrity even when hydrogen is being converted into carbon, even when carbon is being converted into neon, even when neon is being converted into oxygen and then silicon and then iron. The star will still probably hold together if the mass is high enough in the first place. And that is why with a high mass star it might make it all the way to iron. Our Sun won't because it's not massive enough. It'll effectively die and become a white dwarf before that happens. And a white dwarf will be probably mainly made of carbon. But with a high mass star, let's say 10 times the mass of our Sun, gravity can keep it together and keep these phases of nuclear fusion going, perhaps all the way to iron. If it makes it to iron, it can't go any further. It can't fuse iron and release any more energy. So at this point, the core can collapse. And it might collapse in a matter of seconds once it gets to that particular point. If the core collapses, the rest of the star simply piles in on top of it. The star will crush the core down to a very small compact object, and in the process shock waves will rebound off that core and absolutely rip the rest of the star apart in a catastrophic supernova explosion where all the material, or essentially all the material, is ejected back into space. So a small part of the star will be compressed right at the core, but most of the star will be in the shockwave rebound that simply redistributes all of the star's material back into interstellar space, as shown by this wonderful picture taken by the Hubble of the Crab supernova remnant. Trying to work out the energy, well, it's a back of the envelope calculation can tell you, roughly speaking, how much energy is involved, because you can simply say for a star of roughly this mass, literally just how much energy would it take to take each atom in the star and remove the atom to infinity. It's effectively a simplistic way of saying what sort of ballpark energy would it take to explode a star. Just how much would it take to pull the star apart if gravity is trying to hold it together. How many joules of energy are required? Well, you can do this on the back of an envelope and convince yourself that you would need 10 to the power 44 joules. And of course, most people aren't very happy with the idea of a joule because it's not necessarily a convenient energy unit for most of us. So let me put that in some sort of a context. If you imagine the total energy output of the sun, not the tiny amount that actually arrives at Earth and keeps us warm and has done for billions of years, imagine the total amount of energy from the sun that's heading off in all directions. And remember, it's doing that second by second by second, and will do that for something like 10 billion years in total. If you imagine adding up all of the energy that the sun has produced and all the energy it ever will produce over its entire 10 billion year lifetime, that adds up to about 10 to the 44 joules. In other words, in a supernova, it's effectively saying take the entire energy output of a star for billions of years and release it in a few seconds. So we shouldn't really call a supernova an explosion, because the word explosion really just doesn't do it justice. And it's during the melee of a supernova explosion, when all of this energy is released, that's how we get elements beyond iron. It's not part of a star's life in which elements are fused in order to release energy. Here the energy is in the supernova, and the supernova generates sufficient energy that iron can be fused together. It takes energy to fuse iron into heavier elements, and that energy comes from the supernova. So all of the elements generated during the star's life and its spectacular death are ejected into interstellar space. Yes, a small amount of matter ends up in the core, but most of the matter ends up being generated into space, thrown out into space. So everything that we see beyond iron could have been made in a supernova explosion to explain the existence of these elements beyond iron. It's also hypothesized that perhaps some more exotic phenomena such as black holes or neutron stars might also be responsible for some of the heavier elements, but certainly supernova will generate elements heavier than iron. So that means our sun certainly cannot be a first generation star. Quite definitely our sun was not born from the material that was generated in the Big Bang only. Our sun must have been generated from a cloud of hydrogen and helium and a whole load of other elements. If we want to explain why the Earth's crust is scattered with 90 or so elements all over the place, and our bodies have got dozens of elements inside them, then the sun cannot be a first generation star. Some star was born, lived, died, probably in a supernova, and seeded the surrounding space with the heavier elements, which went back into the hydrogen cloud, which then formed another star, which then lived and died and generated heavier elements, which then cycled round again and again and again. So our star might be fourth generation, fifth generation, sixth generation, to explain the sort of abundance of heavy elements that we see on Earth. One thing to bear in mind when you think about the atoms in your body, you don't own those. They were made probably in a supernova. The carbon in your body was made in a supernova. They died in a supernova, were generated, redistributed into space, and eventually found their way into the sun and eventually found their way into the Earth. So you are simply borrowing those atoms for a little while. Atoms are very close to being eternal. The atoms are billions of years old. You happen to be using them for a few decades, or maybe 100 years if you're lucky. And eventually your atoms will get recycled back and will eventually go back to making another star, and somebody else will use them. So remember, the atoms in your body are only on loan for a little while. This is an indication of where most of these elements have come from. You could in principle update it with, yes, we've got more recent knowledge about black holes and neutron stars, but you can see that the lighter elements were made either in the Big Bang or possibly via other mechanisms. Small stars might make some of the lighter elements, large stars will make some of the intermediate elements, and supernova will be making a lot of the heavier elements. And right in the bottom right hand corner there are the unnatural elements, the ones that are man-made, that if they were made in a supernova they would have decayed long ago, and so we don't expect to find them on Earth. Let's come back to what happens after the supernova remnant, after all this material has been blown away into the interstellar medium. What is left behind? Something that's been compressed to a very small volume before the shockwave sends the rest of the material out into the void. Well, the object that's left behind might be something close to a solar mass, but it's not going to be large. A white dwarf, for instance, the ultimate fate of our sun, would be perhaps the size of the Earth. But the object we're talking about here in a supernova might be only kilometres or so in size. A neutron star, for instance, if it was some 5 kilometres or 10 kilometres or 20 kilometres in diameter, the size of a city, then that would be a neutron star. A small, very compact object, still very massive, the mass of our sun, but only kilometres in size, so clearly extremely dense. It is hypothesized that a neutron star might actually have a solid crust around a liquid core. That's been deduced from looking at radio emissions of neutron stars. Radio emissions can be pulsed, and the frequency at which the pulses come out depend on how fast the neutron star is spinning. And if we measure the speed of those pulses, we can find that the speed of rotation of some neutron stars changes. And we think it changes because of changes to this solid crust that's surrounding a liquid interior. Slightly different from the way the Earth works, but the same idea of if we have an earthquake, it can change the spin of the Earth. Hence, if we have a solid crust to a neutron star, if that changes, a star quake if you like, then it can change the spin of a neutron star. So how fast do these neutron stars spin? Well, if they produce radio waves, these radio waves can pulse at the rate of the spin of a star. So let's have a listen to some of these so-called pulsars. This one is rotating at about once per second. So its period is 814 milliseconds. That is quite incredible in itself when you remember that the star has about the mass of our sun. Our sun rotates once a month. This one is rotating a little faster than once per second. Let's go to a slightly faster pulsar. This is the Vela pulsar, rotating more than 10 times a second. Similar mass, very fast rotation. What about the Crab Nebula? now rotating so fast we can hardly hear the individual pulses because they're coming in 30 times per second. Not the fastest pulsar out there. This is going to get a bit ear-rending even over Zoom. Let's go to a faster one. Rotation period of 5 milliseconds, 200 rotations per second. One of the fastest on record is this one. A rotation period of 1.5 milliseconds, one of the fastest pulsars out there. It is thought that they can't be much faster than that, because if it's spinning at 1,000 times a second and it's a few kilometers in size, then the surface must be moving at something close to the speed of light. So we can't have things spinning much faster than that. But one of the interesting things is that I've got the period down there as 1.5 milliseconds, but actually we know it much more accurately than that, because we can watch these pulses come in and time them over many seconds, many minutes, many hours if we want to, and get a very precise value for the frequency. And this one, for instance, is 1.5578064488727 milliseconds. That gives you an idea of how accurately we know the rate of pulses and hence the rate of rotation. And now you can see that we don't need much of a change, for instance a quake on the surface to redistribute the crust to change its rotation slightly. We don't need much of a change to see a difference, because we can accurately measure the rotation speed of these pulsars to, I'm not even sure how many decimal places that is, some 14 decimal places or so. So studying pulsars is a very interesting field of astrophysics, because it gives us effectively physics under very extreme conditions. But a neutron star isn't the ultimate fate of what might happen when a massive star collapses. If the star is really massive, then the contraction of that object at the centre before the shockwave rebounds and sends the rest of the star off into the interstellar medium, that can really win. So neutron stars form because ultimately when we start pushing things together, well, the protons turn into neutrons via a process I'm not going to talk about, and we are pushing neutrons as close together as they want to go. Neutrons really don't want to get any closer than effectively touching each other. And that's why ultimately the star ends up as a few kilometers in size. But gravity, if it's strong enough, will force them together. Neutrons don't want to get close, but if gravity is strong enough, it will overcome any objection that a neutron has of being pushed up against other neutrons, and they will be crushed together. And nothing that we understand at the moment can then stop the gravitational collapse going any further. This, of course, is the stuff which sounds like science fiction. This is what black holes are. Once neutrons no longer are able to resist gravity, we don't know of anything that can stop gravity, so we just assume gravity crushes all that matter down to a point, down to a singularity. We don't know that's what happens, but the point is we don't know of anything that can stop it. Our knowledge is still incomplete there. So now we know black holes exist. They were hypothetical for a while, but now we've seen gravitational waves from merging black holes. We've seen the accretion disk around black holes. We can't see black holes directly, but any matter that's falling into a black hole can get hot enough to emit electromagnetic radiation from the region just outside the event horizon of a black hole. And so we can see evidence that black holes exist from matter that is just outside the event horizon, matter that is heated by falling into a black hole. So there's plenty of observational evidence that they exist, but of course we still have a long way to go to understand everything about these enigmatic objects. So just to recap in words, I've been telling you about birth, life and death, talking about how nuclear ignition starts when a hydrogen cloud collapses, and how, because iron is the ultimate nucleus that can be made in star life, we have to look at star death before we can understand the heavier elements. Let me just summarise that graphically, just because it's easier to think about pictures than it is to think about words sometimes. A cloud of hydrogen might collapse into a small star. When the hydrogen runs out, the star starts to compress, which starts new nuclear reactions and puffs the star up to a red giant. If there's not much gravity there, the outer layers can be lost into a planetary nebula and the resulting core becomes a white dwarf, the ultimate fate of our Sun. But if the collapsing cloud of hydrogen generates a large star with a mass perhaps 10 times the mass of our Sun, then the idea of what happens when the hydrogen runs out, well, the helium starts to burn. When the helium runs out, that starts producing carbon, which starts to fuse into heavier and heavier elements, possibly all the way up to iron. And once we reach iron, core collapse results in a supernova, which blows a lot of material away. And the final star at the core of the supernova might be a neutron star, or, if gravity is strong enough, a black hole. But one thing we must remember is that the white dwarf or the neutron star or the black hole only represent a small amount of the original mass of the star. Most of it gets blown away as a planetary nebula or as a supernova remnant and recycled back into the interstellar medium, where it's reused by another star. And this process will continue for millions or billions of years until all the hydrogen runs out. All the hydrogen that was made in the first 3 minutes of the Big Bang will ultimately run out. It'll take a few trillion years for that to happen, and during the next trillion years or two, this cycle of stars condensing from a molecular cloud, making new stars, which then reseed heavy elements back into the interstellar medium, round and round and round we go. That will continue many, many, many times until all the hydrogen is used up in a few trillion years, at which point there will be no more stars. And once all the stars have come to the end of their lives, all the stars will go out, and this beautiful cycle will eventually come to an end. Thank you for listening.